Now, in this mini lecture, I'm going to show you how we begin to work with correlation analysis and simple regression analysis. Let me remind you from the previous lecture, and I think Orris probably talks about this in his chapter 12 text as well. Let me remind you that correlation analysis is a measure of association, the degree to which two variables are associated with one another. A point that I don't think Orris makes explicitly in his text is that in the Pearson correlation analysis, we are looking for a measure of linear association. That won't really be relevant in this mini lecture, but in a later mini lecture, you'll see where the notion of linear relationship really becomes so key, as opposed to just saying that two variables are associated with one another. So these are data from the textbook that Orris uses in chapter 12, and the X variable here represents the total number of sales calls that a salesperson made. You can see here X equals the number of sales calls, so this is the X column, okay? And then the Y column has to do with how many dollars, or with how many dollars of sales did that salesperson generate. Okay, so variable X is the number of sales calls, and variable Y is the total dollars of sales calls. Okay, so if we look down here at the bottom, the average number of sales calls that each salesperson made was 37. And the average dollars that each salesperson generated was, I believe, $7,500. Or I'm sorry, $75,000. Okay, all right. So now we ask the question: I wonder if the number of sales calls that a salesperson makes is associated with how many dollars of sales that he or she generates. Let me go back and restate that once again. And I want you to listen real closely to my terminology and the research question that I ask. Okay? I wonder if the number of sales calls that a salesperson makes is related to or is associated with how many dollars of sales that salesperson generates. Hopefully it stands to reason, if you think about it, that the more sales calls a salesperson makes, the higher the level of sales that the salesperson should generate. So we consider that to be an empirical question, and we can identify the degree to which these two variables of interest, number of sales calls made and the total dollars of sales generated, we can empirically assess that with the Pearson correlation coefficient. Just for saving time, I'm not going to actually run the Pearson correlation coefficient here. I'll do that later. I've already conducted that test, and we can go to our output, and we see here, this is the correlation matrix. This is the output when we conduct the Pearson correlation coefficient in Megastat. Now, I only want to direct your eye at this point to this variable here, 0.893. And what that number indicates is that the Pearson correlation coefficient between our two variables of interest, X and Y, and remember, X is how many sales calls the salesperson made, Y is how many dollars of sales the salesperson generated. The correlation between variable X and variable Y is 0.893. Now, I want to use that 0.893 to frame for you that from a calculation standpoint, the highest value that the Pearson correlation coefficient can take on is 1. So if two variables are perfectly correlated with one another, they would have a correlation of 1. If two variables were completely uncorrelated with one another, then they would have a correlation of 0. So if you think of correlation moving along a continuum from 0 to 1, you can see here that when two variables are correlated 0.893, that suggests that they're strongly correlated with one another. Finally, I want to direct your eye down here to this portion of the output. This is one of the few things about Megastat that I don't care for, but it nevertheless is how ORIS has the program set up. And if you see here, the first row is, you'll see plus or minus 0.444 is the critical value at the 0.05 level for a two-tailed test, and 0.561 is a critical value in a two-tailed test at 0.01. So what this means, and we're going to focus right now just on the 0.05 level. What this tells us is that anytime there's a correlation, and I'm going to say in an absolute value sense, anytime there's a correlation in our correlation table that has a value of 0.444 or above, those two variables are statistically significantly correlated with one another. In other words, we would reject the null hypothesis being that variables x and y are not correlated with one another. We would reject the null hypothesis and conclude that variables x and y are correlated with one another. Thus, we would conclude that there is a correlation between the number of sales calls that a salesperson makes and how much he or she generates in sales, in terms of dollars of sales. Now, I should have mentioned this point earlier, but let me make mention of this before we close off this mini lecture. I asked the question here, how are our variables of interest scaled? Well, if you think in the case of the number of sales calls, that's a ratio variable. Why? Well, it has a true and absolute zero. In other words, the fewest number of sales calls that a person could make is zero. It has a true and natural zero, and the distance between, let's say, 2 sales calls and 3 sales calls is the same distance as that between, let's say, 18 sales calls and 19 sales calls. So we know for sure that our x variable is ratio and scale. Same goes for our dollars of sales here, okay? Dollars of sales has a true and natural zero. It would be $0 of sales. So here we're working with two variables, each of which are, in this instance here, scaled ratio. It could be interval as well. But we're working with two interval or ratio scaled variables, and we're trying to figure out, are they associated with one another? Are they related to one another? And what we find is, going back to our computer output, is not only are they correlated with one another, they're actually strongly correlated with one another. Thanks.